Welcome to the Deep Dive. Today, we're taking a really fascinating look into the journey and, the thinking of Greg Brockman, co-founder of OpenAI. Our source material is mainly a recent YouTube interview where he got really candid about everything, from how he started coding right up to his vision for AI's future. And our mission here is pretty clear. We want to pull out the key insights, those sort of nuggets of knowledge from that conversation. Think of it as a shortcut to understanding one of the key minds behind, well, what's arguably one of today's most transformative technologies.
Exactly. And we're not just looking at what happened in his career. What's really interesting, I think, is digging into the why certain decisions were made and what that tells us about innovation, about self-learning, and really the whole process of building things in this field.
Okay, so let's kick things off with something maybe a bit surprising. Before all the AI stuff, Greg Brockman actually thought he'd be a mathematician.
Yeah, he was inspired by figures like Gauss, the historical giants. He was looking for impact on a huge time scale, thinking like 100, 200, even 300 years out. Really grand ambitions.
But then reality sort of intervened. A practical problem came up. After high school, he was writing a chemistry textbook, of all things.
Right, and a friend basically told him, look, trying to publish a physical book like that, it's a nightmare. Especially self-publishing.
His friend's advice was simple. Make a website instead. Seems small, but that turned out to be a pivotal suggestion.
Absolutely. That led directly to what he calls his magic moment with coding. He started teaching himself PHP using W3 Schools. Lots of people probably remember that site.
Oh yeah, classic.
And he built this simple little thing, a table sorting widget. And that's when it clicked for him. With those obscure math proofs he'd been thinking about? Maybe, 3 people in the world would ever truly get them.
Right. Very niche.
But with programming, even if people didn't see the code itself, the program, the thing he built, could actually help lots of people. It brought an idea to life in a tangible way.
And that sparked this major realization for him. He basically said, forget about that 100-year time horizon. I just want to build. It's a real shift from pure theory to just, making stuff. So this drive to build things led him pretty quickly to Stripe. And how he got there is kind of a story in itself.
It really is. He got a cold email while he was still in college. He'd apparently impressed people at both Harvard and MIT. He transferred to MIT after dropping out of Harvard, so clearly making waves.
Definitely stood out. So he joined Stripe, employee number 4, I think.
That's right, number 4, and eventually becomes their first CTO. He was there as they grew to about 250 people. Those early days were incredibly intense, but also really foundational for his whole approach later on.
Now, there's that kind of famous story, maybe an urban legend, about the coffee cup installation at Stripe.
Ah, yes, the idea they literally sat behind customers, watching them use the product.
He clarified that recently. He said, yeah, they were obsessed with customers, but that specific scenario only happened to be a handful of times, not a daily thing.
Good clarification. The real intensity wasn't about lurking over shoulders. It was this relentless customer obsession they had, mainly through constant communication on GOT, their internal chat.
Yeah.
And a great example of this and their sort of mindset is the Wells Fargo integration story.
Oh, right. Tell us about that. They were told it would take how long? 9 months.
9 months, yeah. That was apparently the standard timeline back then.
But the Stripe team, they didn't just accept that, did they?
Not at all. They treated it like you said, a college problem set. They just dove in. And unbelievably, they basically finished it in 24 hours.
24 hours instead of 9 months? That's incredible.
But it wasn't smooth sailing,
All
right? No. He described this frantic scene trying to fix bugs live with the person doing the certification. They failed the first time, quickly rescheduled for 2 hours later, fixed the remaining issues, and then passed. Just sheer willpower and focus.
Wow. So what's the bigger takeaway from that frantic 24 hours?
It really comes down to first principles thinking. They didn't just accept the 9-month answer. They asked why. They broke the problem down, questioned the assumptions, and found all this unnecessary overhead and constraints that just weren't relevant anymore. And that mindset, questioning the status quo, is just so critical, maybe even more critical now in AI, where things change so fast. If you just accept limitations without asking why, you get left behind.
That makes sense. And related to that ability to learn and adapt quickly, another big theme in his life seems to be independent study. It pops up again and again.
Yeah, it's a really consistent thread. From high school through sabbaticals later on, he seems to have really honed that skill of teaching himself complex things.
Why do you think it worked so well for him?
Well, he gave this great childhood example. He learned algebra back in 6th grade. Then in middle school, he used online courses to basically blast through 3 years of high school math. in just 1 year. Right. And because he did that, he could then take university-level courses much earlier. It's this compounding effect. You invest deeply on learning something foundational, and it just accelerates everything that comes after.
So his advice is pretty straightforward on this.
Very, basically. Yeah. If you have an opportunity to explore and you have a passion, just go deep. But he's also realistic, acknowledges it's not always fun. You hit walls, you have to push through.
And this wasn't just for math, right? He applied the same approach to machine learning later on.
Exactly. Around 2013, 2014, he decided to really dive into ML. And this wasn't just reading papers. He went out and built his own GPU rig. We're talking Titan X cards back then. He even assembled it himself.
He tweeted a picture, didn't he, in 2015?
Yeah, documented the moment.
Yeah.
It just shows, when you have that passion, that drive, it can really push you past the usual ways of learning. You just figure it out, hands-on.
Okay, so he teaches himself ML, but before OpenAI, he actually had a moment where he felt kind of disillusioned with AI.
That's right. He tried building a chatbot earlier, and it just didn't work out well. Left him feeling a bit skeptical about the whole field at that point.
So what brought him back? What was the turning point?
For him, it was reading Alan Turing's original 1950 paper, the famous one, Computing Machinery and Intelligence.
What with the Turing test?
Yes, but it wasn't just the Turing test that grabbed him. It was a less famous idea in that paper, Turing's concept of a child machine. The idea wasn't to program rules explicitly, but to create a machine that could learn through rewards and punishments, like how a child learns, through experience.
And the implication of that, that's pretty profound.
Hugely profound. He framed it as, what if the machine can understand things and solve problems that you yourself cannot understand? That's a total game changer in how we think about computers.
So Turing provides the theoretical vision. What made it seem practical?
AlexNet. Definitely AlexNet in 2012, winning the ImageNet competition. This deep learning model just blew away decades of traditional computer vision research. That was the moment, he said, when deep learning started tearing down the walls between departments. It was concrete proof that this learning approach, this sort of Turing-esque vision, could actually work in the real world and work spectacularly well.
It's wild that the core ideas of neural nets go way back, like 1943 with McCulloch-Pitts, and the field had those deep learning winters.
Yeah, periods where progress stalled and critics would say, there are no new ideas here. You're just throwing bigger computers at it.
But Brockman's reaction to that was different.
Completely. His reaction was basically, yes, that's exactly what we need to do. He saw that the whole history of computing was, in a way leading to this point, building machines that could tackle problems humans couldn't, machines that could learn. He felt all the pieces, the theory, the compute, the data were finally lining up. The time was right. Now we just need to build. Sometimes scaling is the innovation.
Okay, so fast forward. OpenAI is founded, they're building. In 2022, he writes this post, "Time to be an ML engineer." What was the point he was making there?
He was arguing that great engineers are just as vital to progress in AI as great researchers. Ideas are crucial, obviously, but they simply will not live and see the light of day, especially at the massive scale. OpenAI works at, I think, 100,000 GPUs without world-class engineering to actually build and run these systems.
He mentioned the Ilya-Alex relationship, right? Sutskever and Krzyzewski.
Ilya Sutskever and Alex Krzyzewski from the AlexNet days, but also presumably the dynamic between researchers like Ilya and engineers at OpenAI. It highlights that essential partnership.
Yeah.
You need both deep research insights and the ability to implement them reliably at scale.
But he also mentioned there were challenges, some friction between research and engineering early on at OpenAI.
Definitely. It came down to different mindsets. Engineers naturally value clean interfaces, abstractions, good software practice. But researchers, working with these cutting-edge models where performance is incredibly sensitive, often needed to understand everything, every detail, because tiny changes could break things in unexpected ways.
So different priorities causing roadblocks. How did they solve that?
The key, he said, was fostering technical humility among the engineers. That meant really listening to the researchers, understanding the why behind their approaches, even if it seemed counterintuitive based on traditional software engineering. You couldn't just impose standard abstractions. You had to deeply understand the research problem first, then figure out the right way to build the systems and tools. It's a lesson in respecting cross-disciplinary expertise.
Let's talk about scale in a different sense, the user scale. Those OpenAI launches were just explosive. ChatGPT getting 1 million users in 5 days.
And then GPT for image gen hitting 100 million in 5 days. Just staggering numbers.
How did they handle that kind of viral growth?
He said those periods echoed very similarly. They were intense, all-hands-on-deck moments. And critically, they often had to make tough choices, like pulling a bunch of compute from research.
So sacrificing some future research capacity for immediate user demand.
Exactly. He called it mortgaging the future, basically, to make sure people could actually experience the magic when these things went viral. It's a high-wire act, balancing today's users with tomorrow's breakthroughs.
There's a funny story about the GPT-4 launch demo too, right?
Yeah. The demo involved showing it could understand a hand-drawn sketch of a website. But apparently his own handwriting was so bad the AI couldn't read it. His wife had to step in and draw the joke website for the demo.
Huh? That's great. He also talked about vibe coding. What did he mean by that?
It's this idea of interacting with AI, not by writing precise code, but by giving it a general direction, a vibe, like make a website that looks kind of like this, but for selling dog toys. He sees it as this amazing empowerment mechanism.
And how does he see that evolving?
Well, right now it's mostly interactive. You give it a vibe, it generates something, you refine it. But the future, he thinks, is more agentic. Imagine not just one AI, but hundreds or hundreds of thousands of AI agents working semi-autonomously, like cloud-based coworkers, tackling tasks based on high-level goals. That's a pretty radical shift from today's coding.
And this ties into another shift. He mentioned AI not just for building new apps, but for transforming existing ones.
Precisely. Moving beyond cool new demos to tackling the really hard, serious software engineering problems. Things like migrating ancient legacy code bases or updating huge libraries across an organization.
The kind of stuff that's really tedious and not very fun for humans, as you put it.
Exactly.
Yeah.
AI could automate away a lot of that drudgery, freeing up developers for more creative work.
Okay, let's focus on Codex, their code generation model. How does having a tool like that actually change how you write code day to day?
So a key insight he shared was really interesting. The way you structure your code base determines how much you can get out of Codex. It's not magic. You have to work with the tool's strengths.
And what are those strengths and weaknesses?
Models like Codex are surprisingly good at handling lots of fiddly details, boilerplate code, that kind of thing. But they aren't yet as strong as humans at grasping really deep, abstract architectural concepts. They have lopsided strengths, as he put it.
So how should you structure code to leverage that?
The recommendation is to build using smaller modules that are well tested. Keep things contained, with quick, rapid tests for each piece. Then the AI can shine at filling in the implementation details within those modules and running the tests constantly. Humans can then focus their energy on the higher-level design, the architecture connecting those modules.
It sounds a lot like just good software engineering practice.
It absolutely is. Things like modularity and thorough testing are textbook good practice. But let's be honest, humans often cut corners on this stuff, especially under pressure. Models, though, they care way more about this structure. Why? Because they might run the tests 100 times or 1,000 times more than a human would during development. They need that clean structure and rapid feedback loop.
So maybe building code bases that are easier for AI to work with actually makes them better for humans, too.
That's the fascinating implication. If you structure your code almost as if you were explaining it to a more junior developer, clear modules, good tests, you might get the most out of the AI and end up with code that's way more maintainable for everyone else.
And it's having a real impact.
Oh, yeah. He mentioned Codex writes something like a low double-digit % of OpenAI's internal pull requests entirely by itself. And externally, they saw, I think it was 24,000 PRs merged on public GitHub in a single day that were enabled by Codex. That's significant scale.
Okay, but building and running these massive AI systems isn't easy. Let's talk about reliability and scaling challenges.
Right. This is a huge ongoing issue. As these AI tasks get more complex, take longer, use more GPUs, the chance of something failing, a hardware glitch, a network issue, goes way up.
And restarting isn't always simple, especially for these complex, long-running agents.
Exactly. You talked about this ladder of complexity. Simple pre-training. You can probably recover from checkpoints, though even that isn't trivial.
No.
But complex reinforcement learning systems, maybe interacting with external tools, managing their state, and recovering gracefully from failure is a massive headache. Language models have state you can save, but what if the agent is using, say, a web browser? That state is external and volatile.
This complexity led to a really interesting question from Jensen Huang at NVIDIA that Brockman addressed.
Yeah, Jensen basically asked, how do you design the infrastructure, the hardware, for a future with incredibly diverse AI workloads? You'll have these deep research agents needing tons of sustained compute, But also maybe low latency, always on companion AIs like an R2-D2. Totally different needs.
How do you build for both extremes?
Brockman admitted it's mind-boggling. The sort of naive answer is maybe you have two types of specialized chips or accelerators. One optimized for raw compute throughput, one for low latency.
But that has its own problems.
Big problems.
Yeah.
How do you predict the ratios you'll need of each type? Demand shifts constantly. You risk building out this massive infrastructure where a whole part of your fleet that's just useless because the workload mix changed. That's incredibly expensive.
But he had an interesting counterpoint about how engineers adapt.
Yeah, his perspective was that engineers are resourceful. If you give them a fleet that's maybe misbalanced for the current need, they'll often find ways to utilize those resources anyway, even if it's not perfectly optimal. It might cause some pain initially, but they figure it out.
He mentioned mixture of experts as an example.
Exactly. That's an architecture where you have many specialized subnetworks, or experts. One way it's implemented takes advantage of GPUs having lots of memory, DRAM, but maybe not using all their compute cores intensely. So they fill that unused memory with more parameters, more experts, without actually needing more raw compute power. It's a clever way to use the hardware you have.
So what's the bottom line on specialized hardware?
He thinks homogeneity, having mostly the same type of hardware, is probably the best default because it's simpler. But as the cost of this infrastructure becomes totally eye-watering, then purpose-built accelerators start to make more sense. But it's still an open question, partly because the research itself is moving so fast. What seems optimal today might not be tomorrow.
Looking ahead then to future models, say GPT-6 or beyond, what's the main bottleneck now? Is it still just compute? Or data, algorithms, power, money?
This is really interesting. He said basic research is back. For a while, the focus was heavily on scaling up the existing transformer architecture. But now, algorithms are becoming the long pole, the main limiting factor for the next big leaps. Of course, you still need to keep everything else, compute, data, power, funding, in balance. You can't neglect any one piece. But fundamental algorithmic breakthroughs seem to be where a lot of the potential for future progress lies.
And this connects back to their investment in things like reinforcement learning.
Yes, absolutely. He described looking at GPT-4 initially and thinking, okay, is this an AGI? Clearly not. But it's actually hard to say exactly why not. It felt incredibly fluent, but it would still go off the rails sometimes.
Why do you think that was?
His analogy was that it was like someone who had just read all the books about the world, but had never actually experienced it itself. It lacks grounding, a true understanding derived from interaction. So that realization drove them to push really hard on a different paradigm, like RL, which involves learning through trial and error, through interaction, until they got it to work effectively. And he mentioned there are other very clear missing capabilities. They're still actively researching and pushing on. It's about identifying those fundamental gaps.
Jensen Huang had another tough question. How will software development workflows change when engineers are building on top of these future AGIs?
Brockman offered a nuanced take here. He said, while some people imagine a single all-powerful AI in the sky, the evidence seems to be pointing more towards a future with a menagerie of different models.
Meaning lots of specialized AIs.
Maybe domain-specific agents, or models fine-tuned for particular tasks. This could have advantages like different costs for different tasks. Maybe a small, cheap model for simple queries, a giant one for complex reasoning. Plus techniques like distillation, where you train smaller models based on larger ones. So developers might be orchestrating collections of AIs rather than just talking to one big one.
And wrapping it all up, what's the grand vision driving all this work at OpenAI?
It's ambitious. He talked about creating an economy fundamentally powered by AI. Not in improving existing things slightly, but aiming for something like 10x more activity, 10x more economic output, 10x more benefit to everyone, a fundamental expansion of what humanity can achieve. A key part of that vision is dramatically lowering the barrier to entry for innovation. He specifically mentioned fields like healthcare and education, areas that desperately need breakthroughs but also require deep domain expertise, careful thought, responsibility. The idea is that AI can empower people with that expertise to build transformative solutions that just weren't feasible before.
So if we boil down this whole deep dive, the core themes from Greg Brockman's perspective seem to be this relentless drive to just build, combined with that first principles thinking to break through constraints, and this crucial ongoing dance between cutting-edge research and hardcore engineering.
Absolutely. And that leads us to a final thought, maybe something for you, the listener, to consider. If AI really is changing not just what we can build, but how we build it, and even who gets to build, what are some of those long-standing problems in your own field, the ones that are tedious or unfun for humans? Could they soon be tackled by these evolving AI systems? And maybe more excitingly, what entirely new opportunities open up when the cost and complexity of creating really powerful, beneficial solutions start to fall dramatically? What could you build?
Some powerful questions to think about. Thank you for joining us on this deep dive. We hope you found it insightful, and we encourage you to keep exploring these fascinating ideas.
This was the Gist Podcast. If you liked it, please leave a like and subscribe to this channel.